Right now, the GPS satellites orbiting Earth are running their clocks slightly faster than the clocks on the ground. Not because of a manufacturing defect, because time actually moves faster at altitude, away from the pull of gravity. If engineers didn't correct for this every single day, your navigation would drift by roughly 10 kilometers. We fix this so routinely that nobody talks about it, but what it means is that time travel isn't theoretical. It's happening, just not in the direction most people imagine. The question isn't whether time travel is possible. A version of it already is. The question is whether we'll ever be able to do it in a way that's meaningful, in a way that changes anything. And the honest answer takes you somewhere most people don't expect. What Einstein actually said in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that didn't just change physics, it changed what time is. Before Einstein, time was assumed to be a fixed background, a universal clock ticking at the same rate for everyone everywhere. Newton had built an entire system of physics on that assumption, and it worked beautifully for centuries. Einstein showed it was wrong. Time, he demonstrated, is not fixed. It bends. It slows and speeds up depending on how fast you're moving and how strong the gravitational field around you is. Not as a metaphor, as a measurable, testable, physical fact. The faster you move, the slower time passes for you relative to someone standing still. The stronger the gravity around you, the slower your clock runs. This isn't speculation. We've measured it thousands of times. Atomic clocks flown in aircraft tick slightly slower than identical clocks left on the ground. Astronauts returning from long missions on the International Space Station are fractionally younger than they would have been had they stayed home. Scott Kelly spent nearly a year on the ISS and came back approximately 0.005 seconds younger than his identical twin brother who had stayed on Earth. The numbers are tiny. The principle is not. The forward direction. Forward time travel is physically possible. We already do it. If you travel fast enough or get close enough to an intense gravitational field, time slows for you while the rest of the universe continues at its normal pace. In theory, if you could travel at a significant fraction of the speed of light, you could leave Earth for what feels like a few years and return to find decades had passed. You would have traveled forward in time. The problem is the speed required. To experience any meaningful time dilation, you'd need to be moving at a substantial percentage of the speed of light. The fastest humans have ever traveled is roughly 40,000 kilometers per hour, the speed of the Apollo 10 capsule during re-entry. The speed of light is about 1 billion kilometers per hour. We are not close. The energy required to accelerate anything with mass to even a fraction of light speed is extraordinary. As you approach light speed, the energy needed to go faster doesn't increase linearly. It curves upward toward infinity. You can get closer and closer, but you can never actually reach it. The speed of light is not a barrier we haven't broken yet. It's a mathematical wall that appears to be absolute. The backward problem going forward is at least theoretically achievable. Going backward is where physics starts to resist in a different way entirely. To travel backward in time under current models, you would need to exceed the speed of light. Since that appears to be impossible, you'd need something else. A shortcut. The most serious theoretical candidate is what physicists call a wormhole. A tunnel through space-time connecting two different points, not just in space, but in time. General relativity, Einstein's later and more complete theory of gravity, actually permits wormholes mathematically. They can exist in the equations. The problem is that every wormhole solution ever found in the math is either impossibly small, instantly unstable, or requires something called exotic matter, a hypothetical substance with negative energy density that has never been observed and may not exist. In 2020, physicists at Harvard and MIT developed a theoretical model for a traversable wormhole, one you could actually pass through. It made international headlines. What those headlines mostly left out was the size. The wormhole in the model was smaller than a proton, and the travel time through it would have taken longer than going the long way around through normal space. Why the universe might not allow it. There's a deeper problem with backward time travel than just the engineering. It's logical. If you travel back in time and change something, you potentially create a situation where your trip never happened. You go back and prevent your own grandfather from meeting your grandmother. Your parents are never born. You are never born. So you never make the trip. So your grandfather meets your grandmother. So you are born. so you make the trip. The universe can't resolve this. Philosophers call it the grandfather paradox, and it has never been cleanly answered. Stephen Hawking spent years on this problem. In 1992, he proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel into the past in order to keep the universe consistent. He believed the universe essentially doesn't permit closed time loops, not because of any single physical law, but because the cumulative effect of all the laws together makes it impossible. He called it circumstantial evidence for a cosmic censorship. He was also careful to say it hadn't been proven, where that leaves us. Here's what physics can say with confidence right now. Time is not fixed. It bends around mass and speed in ways we've measured precisely. Forward time travel in small amounts is not just possible, it's already happening aboard every satellite we've ever launched. The barriers to meaningful forward time travel are engineering problems, extraordinary ones, but not logical impossibilities. Backward time travel is a different question entirely. The mathematics permit structures that could theoretically allow it, but every path to actually building one runs into obstacles that may not be solvable. The energy requirements are beyond anything we can conceive. The necessary materials may not exist, and the logical paradoxes suggest that even if you solve the engineering, the universe might have something to say about it. Hawking once said that the best evidence against time travel is the conspicuous absence of tourists from the future. It's a joke with a serious point underneath it. If backward time travel ever becomes possible, it presumably becomes possible at some point in the future, which means visitors from that future could in theory be here now, or at any point in recorded history. And as far as anyone can tell, they're not. Maybe that means it never becomes possible. Maybe it means travelers are here and we just can't recognize them. Maybe it means the physics works, but the paradoxes wall off the past from ever being visited. What we know is that time is stranger than it looks from inside it. Stranger than Newton imagined. Stranger than common sense suggests. And the question of whether we'll ever navigate it the way we want to is still genuinely open, which, honestly, might be the most interesting thing about it.